I'd like to go over a few examples of rotational motion. These let's consider, if I can draw, that is. Let's consider a disk that is rotating about its center. So the rotation axis is in and out of the page. Um, Actually, that's not even. We don't even know if it's rotating yet. But what we do know is that there are a number of forces being applied onto the disk. The first force is applied to the right, and let's call that F1, and its moment is the radius of the disk, R. Second force, F2, is applied at an angle like this. This is F2, and we know what this angle is. Let's say theta 2. This, of course, right angle is there. Third force is applied radially, F3, and fourth force is applied like this. This is the top view of all the forces being applied. Now we do know that this distance is r over 2, let's say, and also we are given this distance as r over 2, radius over 2. And we're interested in figuring out the net torque acting on this disk about the center of rotation, about the rotation axis. Now, to figure out the net torque, start with the first force and work your way through. So torque due to F1 is F1 multiplied by its moment R, and it's a negative torque because acting alone it would cause a clockwise rotation, and since the angle is 90, for the sake of completeness I can write this sine 90, of course, which is 1. Second force is F2. Its moment is r over 2. It's the distance from where the force is applied to the rotation axis. This is r over 2, and the angle is sine theta. And acting on its own, that would give us a positive torque. That would give us a counterclockwise rotation rather. Now F3, its moment is r again. It's being applied the distance r away, and the angle is 0, which gives us a 0 for this thing. So the radial force, of course, doesn't cause a rotation, as one would expect. And finally, we have F4. Its moment is r over 2. Once again, the moment is the distance from where the force is applied to the rotation axis, which is r over 2. And acting on its own, this would result in a counterclockwise rotation. Therefore, it's positive torque, and our angle is 90 degrees, so sine of 90 being 1. So that's how you can go about figuring out the net torque in any system. Just take each force multiplied by its moment of arm and the angle that the force vector makes with the moment vector. Now, in example 2, let us consider once again a disk which is rotating about its center. Say the disk has a radius r, and let us say that the disk is rotating with an initial angular velocity omega I. So this is omega I, and we want omega I to drop down to 0, so omega final is 0 in 4 seconds. So we want to bring the disk to a stop in 4 seconds. So initial velocity omega I going to final angular velocity of omega f in 4 seconds. For the sake of argument, if we say initial angular velocity is 400 revolutions per minute, for example, then we can calculate the angular acceleration. This is omega final minus omega initial divided by the time taken, which is omega final is 0 minus 400 RPM divided by 4 seconds. Now here's when you need to convert RPM into radians per second. So that's minus 400 RPM. You need to multiply RPM by 2 pi radians and divide it by 60 seconds to get radians per second. So you end up with 200 pi negative 200 pi over 60 radians per second. So this is your alpha. Your alpha is has a negative value, which makes sense because we are trying to bring a positive angular velocity down to 0. And if the question were how much friction force does one need to apply, so let's call this tangential force, which is our kinetic friction force. So let's imagine this. We have a brake pad and we're trying to figure out how much friction force does one need to apply to bring the disc to a stop in 4 seconds. Well, we use torque, or net torque, is equal to I alpha. This is our Newton's second law for rotational motion. I alpha. I, moment of inertia for a disk, is 1/2 of m r squared. So the disk has a mass m, let's say. So we have I is 1/2 of m r squared times alpha. And alpha you just figured out here. So this is your alpha. So we know alpha. So thus you can figure out how much torque is needed, and torque is equal to force times r. That's the magnitude of the torque. And notice that since alpha is negative, your torque is negative, which means that your friction force is going to be negative, which does make sense because we do need to apply a negative force. That's the force that's the force that would cause a rotation in the clockwise direction to bring this disc to a stop. So having figured out alpha, then it's a trivial matter to figure out the value of the friction force. And again, in doing dynamics analysis for rotational motion, you use the torque equals I alpha, the rotational version of Newton's second law, of course. Right, in the third example I like to do is let's consider a pulley which is fixed with ceiling. We have a rope goes over the pulley and is attached to two masses, M2, M1, and let's say the pulley has mass M0. So now the pulley has some mass, so there's a moment of inertia associated with it. It's a disc shape which has a radius r, let's say. Moment of inertia of a disc, as we've seen a number of times, is 1/2 of m naught r squared. Now let us also assume that m1 is less than m2, so when we release the system one would expect m1 to accelerate upwards with acceleration a and m2 accelerate downwards with acceleration a, and if we go ahead and identify the forces on m1, of course m1g and tension 1. Now tension 1 is the same here, this is T1 as well. Forces on M2 are M2G, and this is T2. Of course we have T2 down here. Now it is important to note that T1 and T2 are no longer equal because our pulley is not massless, it has mass associated with it. So T1 and T2, you cannot set them to be equal, of course. Now let us write, I'll use the blue pen, let me write the Newton's law, second law applied to mass 1. So we have sum of the forces in the y direction is equal to mass of the object times its acceleration. Sum of the force in the y direction is T1 minus m1g is equal to m1a, which gives us T1 is equal to m1 into g plus a. So our first equation. Now let's also consider mass 2. So for mass 2 we have sum of the force in the y direction is equal to mass 2 times minus a, is downwards. So we have T2 minus m2g is equal to minus m2a, or T2 is equal to mass 2 into g minus a. So our second equation. We use the red pen now. Now if we consider a point on the string, this red point there, the acceleration that that point has, at, downwards, is actually equal to the acceleration of this point on the string, which is a, as we show in the drawing. Similarly, the upward acceleration that the magnitude, that is the tangential acceleration that the string has where it's connected, where it touches the pulley, is the same in magnitude as this a down there, because we assume that the rope or the string doesn't slip. Therefore the acceleration of any the linear acceleration at any point must have the same magnitude. So using the red pen, now we can also go ahead and write for the pulley, this is for m naught, that sum of all the torque, since there's no translation, so on the rotation, sum of the torque applied to the pulley is equal to its moment of inertia times angular acceleration. What is the torque on the pulley? We have two forces, T1 and T2, acting on the pulley at opposite, diagonally opposite to each other. Torque due to T1 is T1 times its moment, which is R, and it's a positive torque because it's a counterclockwise rotation, would cause a counterclockwise rotation, minus T2R, that's torque due to T2. That must equal I alpha. I, in the case of a disk, is 1/2 of m naught R times R squared, rather, R squared times alpha. Now alpha I can rewrite as tangential acceleration at divided by r. Okay, so this is alpha, and this of course is this whole term here is my moment of inertia. So you see that, let me grab my black pen, this r and this r squared cancels with these r's, and we end up with t1 minus t2 is equal to 1/2 of m naught, and instead of at I'm going to write a. That's the argument that I used here, that the magnitude of the tangential acceleration of the string must equal the linear magnitude of the linear acceleration of the string where it's attached to m1 and m2. So we have m naught times a. So this is our third equation, and using these three equations now we can solve for t1 and t2, for example, and also a. So we can solve for t1, t2 and a. Three equations, three unknowns. Okay. Alright, in the third example I'd like to share with you, let us consider a shape whose center of mass we know where it is, and this is, let's say, a piece of art that is nailed to the wall through this point. I'm going to call this my pivot point. So and initially the pivot point and the center of mass lie along this horizontal line, and we wish to support this artwork by uh, connecting it using a string to the ceiling. So the artwork is supported by a nail driven right through it onto the wall, and this the tension T applied to the string here. So if our artwork has a mass m, we know where the center of mass is. Once again, let us go ahead and identify all the forces. So we have mg acting down. Remember, weight acts at the center of mass, and of course T, tension, acting up in this way. Now if we know the distance, if the distance from the center of mass to the pivot point is given, let's call that L, and the distance from the pivot point to where the string is attached, let's call that big L, then for equilibrium we make the argument that the sum of the torques must equal 0. Now let us go ahead and figure out the torque. Actually, I forgot, let me back up. There's one other force that acts on this body, and that's the normal force from the pen acting on this artwork. So let's call that the normal force. So the torque about any point must equal 0, and I'm going to choose the pivot point as to calculate the torques about. Why is that? Because now when I consider the force due to the normal force N, its moment is 0, so that it drops out, so this whole term becomes 0. So N is a force that I do not have any information about, so and is not a force that I'm trying to figure out. I'm trying to figure out what T is, for example. Then choose a pivot point where that force acts on the body. That way you eliminate it out of the picture. So we have N times 0 minus mg times little l plus T times big L. So that's the net torque, and that must equal 0, i.e. mgl must equal TL, or T must equal mgl divided by L. So knowing big L and little l, you can go ahead and and figure out what the tension, the required tension needs to be in the string. Right, let me also do a couple of examples on how to calculate the center of mass. Um, let's do the first example where we're interested in. Let's say we have a shape. We have an extended body which is given by mass 1, mass 2, let's say mass 3 and mass 4, and in this case, let's say the problem tells us the coordinates. So the problem gives us the coordinates for each mass. Well, the problem may be in the shape of what is what. Let's say we know x2, y2, and we know x3, y3, similarly x1 and y1, but we do not know x4 and y4. So these we do not know, and the problem may give us all the information except this, of course, and the question may be of the form of what does x4, y4 need to be such that the center of mass would have coordinates of 0, 0, right? So on a Cartesian coordinate system x, y, we want center of mass to be at the 0, 0 point. Well, you use the expressions for x coordinate of center of mass being equal to sum of mi xi divided by mi, but set the whole thing to 0 and figure out what x4 needs to be such that this sum turns out to be 0. Similarly, ycm is mi yi divided by the sum of mi, and that whole thing needs to be 0. So just figure out what y4 needs to be such that this sum equals 0. So it's a simple application, but I've seen people kind of fall into unnecessary traps in solving problems like this. If we are given a shape of an equilateral triangle, it's an extended body in the shape of an equilateral triangle, equal masses at each corner and length L, and we are asked to, for example, calculate the moment of inertia of this object about a rotation point that is in its middle. So to calculate this, since we have an equilateral triangle, we know each angle is equal to 60 degrees. So the center point, if we consider this blue triangle for rotation about the center, then we know that this angle must be 30 degrees because due to symmetry arguments, these are 30-degree angles. And if that's a 30-degree angle, then this distance right there, is called that R. Excuse me, R. To figure out R, why am I interested in figuring out R? Because moment of inertia is the sum of each mass multiplied by its perpendicular distance to the rotation axis squared. So R's are the same in each case. Okay, R's are the same in each case, And R, to figure out R, you look at this red triangle right here, where this is 90 degrees, and if I call this H, I'm sorry, not the, where this side here is L over 2, that's half the length, half the size of each one length, and as you can see, R is equal to L over 2 divided by cosine of 30 degrees by just looking at the red triangle. This angle here is 30 degrees, of course. So moment of inertia then becomes the sum of each mass times L over 2 divided by cosine of 30 degrees all squared. So this is R squared, and since we have same masses, then simply 3 times mi L over 2 cosine of 30 all squared. So that's the moment of inertia of this extended body shaped as in the form of an equilateral triangle rotating about its center. And finally, let me do a couple of examples on vector cross product. Let's say that we have vector f, which is given by minus 7j, and vector r, which is given by 3i plus 5j. Well, what is the torque due to these two vector f with a moment of r? Torque is r cross f. Please make sure you get the order right, which is equal to, you write it out, 3i plus 5j crossed with minus 7j, and that's equal to negative 21k, and that's it. So that's negative 21k is the torque, and the units for torque are of course Newton meter. So negative 21k Newton meter is the torque due to force F with the moment R. Speaking of torques, actually let me also go over something else with you. Let me put you on pause for just a second. Alright, let me let's consider a disk which, let's say, is rotating this way. So we know that the angular velocity vector is pointing up, and say that it gets displaced by angular displacement delta theta. Delta theta in some time delta t. So over a period delta t, the displacement is delta theta from initial position to final position there. And let's say that over this period the angular velocity goes from initial angular velocity to some final angular velocity. So there's a net torque. So there's a net torque acting on our disk. Due to that net torque acting on the disk, the angular velocity of the disk goes from some initial value to some final value, and if we were to take any position on the disk, it undergoes a displacement, angular displacement of delta theta. Now, thinking back to rotational kinetic energy, Rotation kinetic energy initial is um, 1/2 of I omega I initial squared, and kinetic energy rotational final is 1/2 of I omega final squared. Now for the specific case, well, for sake of simplicity, if we assume omega I to be 0, so we have a disk which is stationary, and we apply a torque to it, and as a result of that torque it starts from 0 angular velocity and goes to some final value, and during that time delta t, any position on the rim, which is a radius r away, undergoes an angular displacement, or any position on the disk undergoes an angular displacement of delta theta. Then the change in the kinetic energy, rotational kinetic energy of the disk, simply final rotational kinetic energy minus initial rotational kinetic energy, which now takes the form of 1/2 of I omega final squared minus 0, okay, which is 1/2 of I omega final squared. Now here we have a constant torque acting on the object, which implies that our angular acceleration is constant. Therefore I can use kinematic equations of motion for rotational motion. Since alpha is constant, then omega final squared is equal to omega initial squared plus 2 alpha delta theta, but we argued that omega initial is 0, so this is simply 2 alpha delta theta. Therefore change in kinetic energy rotational is equal to, substituting for omega final squared, that's 1/2 of I into 2 alpha delta theta. I substitute for omega final squared, which is equal to I alpha delta theta. Now I alpha we defined as torque, so that's torque times delta theta. Notice that we end up with delta k rotational is being equal to torque delta theta. Note the similarity of this with delta k is equal to force times delta s. Work theorem, kinetic energy work theorem, where F delta S is work done by the force on the object. So we can therefore say that work done by torque, rotational work done by torque on an object, is equal to torque times the angular displacement. So since work energy theorem tells us that the change in the rotational kinetic energy must equal rotational work done on the object. So rotational work done on an object is given by the torque acting on the object times the angular displacement. So for example, if we have a disk rotating about an axis in and out of the page, perpendicular to the page, and there is a force F acting on the object, the disk, the radius of the disk is r, and we rotate as a result of applying this force. The disk rotates by some angle delta theta. Then work done to rotate the disk is given by torque times delta theta, torque being Fr times delta theta. So you can go ahead and calculate the amount of work and then relate it back to its change in kinetic energy, etc. So it's a useful expression to bear in mind in solving problems. Okay.